Okay, hi everyone. Good morning. So today we have Tom Broadhurst. He comes from the University of the Basque Country, and he is spending a couple of days in the island. So he kindly contacted us to pass through the institute and deliver a talk today. So Tom was a PhD student in the UK. He completed his PhD in Edinburgh in Durham in 1999. Then he moved to, he has a very long trajectory on observational cosmology. He has covered many different topics during his research. His work on large-scale structure, galaxy formation, and more recently, he's been working very actively in lensing, and since the days of his PhD. So after Durham, he moved to Edinburgh. He was in the Royal Observatory until 1995. Then in 1995, he moved to Berkeley. Is that correct?
That's right. Yeah.
Then, okay, he got a faculty position in Berkeley in 1995. Then in 2001, he moved to Tel Aviv University, where he remained until 2011. And in 2011, he happily came to Spain, to the Basque Country, where he's holding a Iker Basque professorship. So I think that's all for the introduction, and if you're ready, we can start now. Okay, thank you.
Well, thanks, Ricardo, and thanks for coming along at relatively short notice. And I hope I can interest you in this new, well, it's an interpretation that's goes back to the late 90s for the nature of dark matter as a light boson. And we're used to, of course, thinking about heavy particles as the default interpretation, usually fermionic. So in this sense, this interpretation takes the opposite point of view, that dark matter is light and bosonic. And then in that way, it can be in a condensate in the ground state, so that it's effectively cold. And of course, we know clearly from large-scale structure, CMB, I know you guys, Alberto, everybody's working in the Planck team here, will be very assured that the dark matter is not relativistic, apart from the neutrinos, but that's just a tiny fraction. So this offers another non-relativistic interpretation, even though the particles, the bosons, are so light, because their occupation number, the number density of these particles, since they're so light, is so large that the ground state is where they must lie. So this idea has been around since Renan Bakana and Wayne Hu described this as fuzzy dark matter. But there have not been any simulations of this, because it's very difficult, relative to n-body work, to follow these macroscopic waves and their self-gravitation and their interference. So this is what we've achieved for the first time. And interestingly, as a consequence of these simulations, we see a lot of non-linear structure, including stable solitons, and also this granular pattern, which distinguishes this form of dark matter from regular collisionless WIMP dark matter. So we have clear predictions. As I say, on large scales, everything happily is the same as cold dark matter. But on smaller scales, depending on the choice of the boson mass, then there's structure on the de-Broglie scale corresponding to that mass. And that can be astronomical scales. So this is the free parameter that we fix. So this work is in collaboration with my two colleagues at NTU, frequently visit them. Justin Sheave in particular has been writing the code for the GPU cluster that's needed to make this demanding calculation. And Zihong Chui is expert on many things, including quantum theory, Professor Chui. And then the observational interpretation of these features is what we've been focusing on, including with my colleague in Bilbao, Ruth Laskos, who you'll know, and Ivan DiMartino, I think Ricardo is familiar with, where we are looking at the oscillation that's inherent to this kind of dark matter, scalar field dark matter. And that can be tested definitively with pulsar timing. So we'll see that there's a variety of ways to test this, and there's this very definitive pulsar method that we just had accepted for PRL last week. So let me just mention that the Hubble, of course, so this is the GPU cluster that they have built in Taipei specifically to make this calculation. So these are a really powerful way of doing parallel processing. Anyway, so as I say, it has some history to it, this idea, and was raised by Nick Kaiser and Lawrence Widrow as early as 1995 as an alternative to n-body simulations. So those days when the worries were about softening lengths and other possible systematic problems with n-body simulations, solving this, we'll see in a minute, coupled Schrödinger equation is formally equivalent to collisionless cold dark matter on large scales, and was raised by them as a way of avoiding the usual systematic problems. But actually it turns out to be more difficult than they had imagined to simulate this. The idea was taken literally by Hu and Barkana, and they noted that a scale of 10 to the minus 22 electron volts would help in suppressing small galaxies, which by this time, in 2000, were realized to be problematic for regular collisionless CDM. So this has the advantage that that scale will suppress structure, and it'll also provide a kind of core, though exactly how nonlinearity alters the collapse of these structures could not be known at that time, as they stated so well in their paper here. So this is where, and there's other numerical work by David Marsh, now in Göttingen, and Joe Silk, and David Spergel, and also last year, Ed Witten, Ostreicher, and Tremaine have written really, and Lam Hui, a really landmark paper about the theoretical foundations of this approach. And they are quoting our simulations to describe the more theoretically the non-linear aspect. So that is putting the whole field on a strong foundation. And since that time, there's been a lot of interest in this idea. Axions are the natural candidate for such a light boson because of this connection with string theory and this notion of an axiverse where perhaps as maybe a discrete mass spectrum over a wide range of scales that could be motivated by string theory. Apparently, obviously this is beyond most of us, but inherent to string theory, and Henry Tai has been impressing on us the connection with string theory. There's an inherent connection there with this misalignment angle, which is effectively the axion. So axions have got a good theoretical basis, and they're of course a light boson. So this is what we published in 2014, and we first showed that on large scales you cannot distinguish statistically between regular CDM and what we term PSI-DM. This is what we called our simulations. So this is because of the connection to the Schrödinger equation. So this is a very demanding calculation because you have to follow the evolution of a self-gravitating wave pattern so that the square of the wave function here is giving you the density of matter in this context, and that of course is an interference effect. So all dark matter in this idea has developed by self-gravity and interference as a huge interference pattern. So it's quite different then conceptually from regular n-body description. So what you have to do, and it's not particularly demanding theoretically, but computationally is very tough, is the Schrödinger equation that is coupled to the perturbations in the density field through Poisson's equation, that the potential, the gravitational potential, then it acts on the Schrödinger equation, and that's where the evolution takes place. And the rate cosmologically of expansion and so on is captured by the scale factor here, A, and this is the mass of the boson. So relative to normal CDM, there's one extra free parameter that you can either set to be very large, and that would then be exactly like CDM, or as we do, we have explored the low mass end so that we can use this mass to hopefully help with the problems that regular CDM faces on the scale of dwarf galaxies. So we needn't have done that. I mean, it would be just as viable to have this at TeV level, but then there would be no need to make this calculation. It would be, in fact, it would be very, very difficult because the wavelengths would be so much smaller. So anyway, so you can see that on large scales, starting from the same initial density field, that there is nothing to distinguish normal CDM modeled here by usual Gadget 2 code from the way that we've implemented this evolving wave function here with GPUs and an adaptive mesh. So now, if we look at in detail within each halo, we'll see a lot of interesting structure that forms on the de-Broglie scale. So that scale is given by the momentum of the material, and we need to follow that scale. So you need to refine this calculation where the momentum is changing quickly, where the momentum is high, and also where the density is high. So this calculation is quite difficult to do. You need two different kinds of refinement. And then, as I say, if you blink between these, I don't know if I can do that here. Okay. Yeah, there we go. So if we flash between them, you can notice that the small scale features, these tiny galaxies, are missing in the wave dark matter simulation here. And that's the desirable effect of having this light boson mass. There is an effective gene scale in this, so that below that scale structure can't form. And that is essentially follows from the uncertainty principle, that you cannot confine material on a scale smaller than given by the uncertainty principle. So just let me do that again. Let's see, flick between the two. Okay. And again, you can see here that I don't know. Yeah. Oh, yes. You can see that all these little galaxies that we're used to thinking about for CDM are missing in the filaments of these simulations, but otherwise they look very similar. Now, within each halo, there is a lot of structure, and particularly when halos collide, there's a radiation of the wave function away from collision. So this has a slight modification effect on the statistical properties of halos. And let me continue. Here's a set of how the wave function evolves from the initial condition. So initially, of course, there's no high frequency structure, so the distribution looks like a low frequency, low amplitude. So these are slices through the simulation, and then over time, the self-gravity develops these virialized structures, and you see what then are halos information. I can actually have a video to show you of the development of the structure. This is here. Let me just do that. Maybe you can see here. So these are some of the time steps in this calculation. There are many time steps, and initially the code runs quite quickly, and then as the dense virial structures form, everything grinds to a halt as we try to. That's why the refinement is necessary, and we can make progress, although we haven't yet managed to simulate clusters of galaxies. They're too large to simulate. But you can see that despite the fact that this is an interference pattern, structure develops in a way that's sort of familiar when you think about the n-body simulations. It's not so on large scales. It's indistinguishable, although rather sharp and with these oscillatory features. So you can see across the filaments there are parallel tubes of enhanced amplitude. Oh, here's another one. So this is actually the same thing from a different angle. Just to give you a feeling for how this thing develops. So you should just think of it as a self-interference pattern under its own self-gravity. So there's no, the gravity is in proportion to Poisson's equation. So what's entirely absent here is any other force apart from gravity. We don't worry about small-scale interactions of whatever these bosons may be. All right. Okay, so I'll go back to where we were. Okay. So that is, it's quite an unusual type of simulation. The pressure term is the complication here. And as I say, this effectively follows from the uncertainty principle. So if you think of, if you describe this as a fluid, then there is this additional stress that's not present with normal collisionless cold dark matter. Collisionless by definition. This has a pressure term. And you can also derive a gene scale, meaning that below this scale there is the structure cannot form. So that's, in other words, the dark matter has an inherent gene scale in this context. So we put that to use to suppress small scale structure. And so the question is, on what scale, what should we choose for this boson mass? And you can see that the profiles of structure that develop in this context are, on average, NFW-like, even though all this granularity is present on the de-Broglie scale. But in the very center, this is really the ground state of the condensate and can't be avoided. This soliton structure sticks out above the general profile and enhances the central density relative to a pure NFW profile. So that would be NFW. And the smaller the halo, the larger is the soliton. Larger in size, but the smaller in total mass. So there are scalings that, I should say that these solid curves here are the theoretical forms for the stable solution of this Schrödinger-Poisson equation. So that coupled equation you can find a time-independent solution for, numerically. And that demonstrates that this feature that we find inside every object is in fact the ground state. So now you can see that there are some really interesting testable predictions now of this model on galaxy scales. And we checked with different levels of refinement that soliton is really there. And we also have this toy model that Justin also wrote the code for. We can start from a set of solitons and have them collide and create a halo of with any combination of potential and kinetic energy. So that we can look at scalings related to the size of the central soliton and the overall mass of the halo in great detail. So we have this ability as well. So to set the boson mass, we can, the soliton in the middle reminds us of the chord profiles of dwarf spheroidal galaxies. So as we know, they are the most common class of galaxy, numerically the most common galaxy. And that their mass profiles the density profile is flat, and the velocity dispersions tell you that. Quite different from a globular cluster where the dispersions are dropping, and when there is no evidence of dark matter. Here, these objects seemingly are completely dominated by dark matter with very large mass to light ratios. So in this context, we have a natural explanation for these chord profiles. And then the question is, can we use the scale observed for these profiles to constrain our free parameter, this boson mass? So this is how we do it. We take the stellar number density and the velocity dispersion, put it in the regular Jeans dynamical equation, and this is what we obtain. So basically, a kiloparsec scale core corresponds to around about 10 to the minus 22 electron volts. So that is and in principle, any dwarf galaxy should provide the same answer, because this mass is what determines the core, and so that has to be universal if this model is to work. So we've chosen here the Fornax galaxy for this purpose because of the quality of the data there. And also there are 3 stellar populations within that of different velocity dispersion, but this is allowing us to double check this. Alright, so once we've set that mass in that way, locally, independent of the simulations, we can then, we have no free parameters anymore. And so we can make these tests. So this is where we are very vulnerable at this point, right? Because everything is either consistent or it will fall apart. So the fact that I'm standing here still telling you about that means that we have found actually quite amazingly good consistency. So this is a typical slice through CDM at the top here. All these tiny little galaxies form all the way back, as we know, redshift of 50. Whereas, in this context, with that choice of boson mass, there are no halos before a redshift of about 10, 11. This is where we start to see our halos. And of course, this is somewhat dependent on the choice of the box. We don't have very large boxes. But the number density of collapsed structures rapidly drops above this redshift. And below that, you can see that all the major halos start to form and correspond to those in a normal CDM n-body simulation. So this is a very interesting thing, because once we completely independently determined that mass scale using Fornax, requiring that we match the core of that object, and then we see that the first galaxies to form in any numbers is around redshift of 10. And actually we have no real evidence for galaxies beyond that, unless there's any news from any of you guys. I mean, I know you're all in the forefront in that respect. So I'd be curious to hear if there's anything, any hint of anything beyond a redshift of 11 or so. Another point to make about those first galaxies is that this dense ground state feature forms first, and the outer halo takes a while to virialize. So here you can see large wave-like perturbations despite the averaging. And that's again different from CDM. It means that quite large masses of around 10 to the 9 solar masses on a scale of 100 parsecs are forming initially, and perhaps could help explain the existence of quasars and other seemingly quite large galaxies at these redshifts. Here's an example that we discovered in this CLASH program that we've been pursuing for the last few years. And you see there that the highest redshift galaxy that we found in that survey is these 3 images here. And this thing is not incredibly small. It's of order of kiloparsec across, and you know, it's a reasonably, despite the magnification, still reasonably visible object. And we have another one that from the year before, redshift 9.6. It was even a little bit larger than that. So these galaxies are not as small as we might have imagined. I don't know how many of those of you are involved with lensing, but just to say that we have really demonstrated that this redshift of 10.8 corresponds to this object, because quite close to it are other objects at lower redshift, these 2 here and this one, and others as well, that give us the scale of this lens. And the larger the redshift of the source, the larger the angle through which the light is bent. And so just by looking at the relative scales, you can tell the difference between the redshift 2, 3, 4, and in this case 10.8. So we've determined this thing not only photometrically but also geometrically. And we've been looking for more of these in the Hubble frontier fields. So we've been working hard on these as well. And we have yet to find anything above a redshift of 10. The highest redshift that we found is in here, this one, this pair of images, quite close to the critical curve, and we have a prediction there geometrically for its redshift. So this is anyway, so the point is that perhaps redshift 9 or 10 really represents a limit, because the magnification provided by these frontier fields was, you know, could have taken us out beyond up to a redshift of 12 in terms of looking for this Lyman break, but we don't find them. And what we do find, there are just a very rather rare and not incredibly faint objects. So that may be already, of course, JWST is obviously the instrument for pushing this. And what we would have, what we predict in this context is that there will be, you know, actually nothing visible above a redshift of 10, 11. Otherwise, we would have to revise this boson mass up quite a bit, and then the cores of the dwarf galaxies locally will be too small. So the smaller the core, the higher the redshift of formation. And that actually has been the problem for warm dark matter. Warm dark matter has sort of failed the same test, because if you're just appealing to temperature rather than this kind of pressure, which is quite different, then to match this large cores seen in the dwarf spheroidals, the redshift of formation becomes too low in the case of warm dark matter. All right, so there does seem to be a turnover here at a redshift of 8. It may correspond to the rather low redshift of reionization that I know that many of you have been working on in the Planck team here. And this is what we favor with from our simulations of wave dark matter, is a rather low redshift of reionization, because all those small galaxies are absent. So above a redshift of 10 there shouldn't be anything, just filaments. So as comparing CDM to wave dark matter, this is the way things will go towards lower redshift of reionization. And yeah, so that's anyway, so we, you know, I think in the interest of time, I'm not going to dwell too much upon the luminosity function work that we've been doing, looking statistically at the formation, but rather just tell you about the definitive predictions. So all this granularity, so this is just the modulation. There's a full 100% modulation of the density structure of any virialized halo in this context. So we have the density can go to 0, it can be double in that range. And azimuthally, we see that, as I showed before, the profiles are NFW outside of the central soliton. And but imagine viewing a multiply lensed quasar through this. You would expect to find small-scale perturbations affecting the magnification of the images, and that's been quite a problem for a long time for a regular CDM. Despite all the small-scale structure, all the tiny galaxies in CDM, when you zoom in to the center here, tidal effects have erased most of those. So in this careful kind of work here, by the CDM proponents, they have stressed that they cannot reproduce the level of difference in brightness between multiply lensed images with these simulations, because in fact they're too smooth. Now in our case, although we have eliminated small scale structure, small galaxies, within the collapse structure we have this non-linear de-Broglie scale interference, and that pattern varies on a time scale of about 1 to 10 million years, depending on the mass of the halo. So effectively it's static when we think about quasars, and we expect that the critical curve will be, as you see here, corrugated by all that fine scale structure in a way that doesn't happen with CDM. So the general lensing theorem that says this image shall be as bright as these two would be violated in our case. So this R factor is a measure of the difference from the case where the theorem, where the halo is smooth. And you see for CDM, this is a very small number, few percent level. So just because there is a small level of structure. But in our case, we expect 40% type flux anomalies. So these flux anomalies will be common, and of all the quasars that have been carefully studied, they do lie above the CDM predictions. These are predictions by Metcalfe and Amara, and the data does lie above that. So, that's one encouraging sign, and we have to look at this in more detail. The critical curves are affected, especially the cusp regions, by all this fine scale structure. And interestingly, Kochanok and Keaton did derive such a critical curve when they try to model this with a general polynomial. So in trying to fit the positions and the magnitudes of these multiply lensed quasars, but they dismissed it as being unphysical. But we see, in fact, that it corresponds very nicely to what we predict. Whereas with CDM, you have to be lucky and have very local, dense features affecting the images. And I think a lot of the careful work recently done with ALMA has shown that there is lenses that there are only at most, one or two, possibly only one small-scale dense structure for every large lens, that's galaxy lens that's been studied. So perhaps that conclusion will follow. Now, in the centers of every galaxy, we cannot avoid this soliton. And so we may look dynamically there for any evidence of increased dynamical motion. These are H1 maps of this analog of the Milky Way galaxy. Some of you may be more familiar than me with this particular object. But in the center of here, as actually with many local well-studied velocity fields, it's interesting to see that there is the velocity, you know, the rotation curve seems to have an enhanced local peak. So you can think of the scale here is about 10 to the 9 solar masses, and the velocities are maybe 200 kilometers a second. And I can show you that this is what we predict. In fact, here are the predictions. This is a little bit complicated, this plot, but what we predict is that from the simulations, that the halo mass, the soliton mass scales with the halo mass to the power 1/3. So in going from, say, 10 to the 9 solar masses of a dwarf spheroidal to our galaxy, 10 to the 12, 3 orders of magnitude means a factor of 10 increase in the central mass. So that's around from 10 to the 8 to 10 to the 9 solar masses for the soliton. And a reduction in scale of the soliton from 1 kiloparsec by a factor of 10. That's inverse with the mass. And that inverse behavior follows from this scaling that is inherent to a soliton. So this is an inherent scaling, and so these numbers that we predict are, I mean, they must follow in this context. So it's the most definitive way of testing this would be looking at the soliton that we predict in the center of our own galaxy. So that's a 100 parsec scale object with a total mass of 10 to the 9 solar masses. And there's some very new interesting work by Portail et al., who have noticed missing mass on that scale from a careful new dynamic study. So we can ask, well, what would this millisecond pulsars that are expected to be detected in the center of our galaxy, how would their timing be affected by the presence of this inherently oscillating bosonic field? And that the time scale for that is just given by the boson mass. So everywhere that there's a clock, including in this room, there should be a very small level of modulation on a time scale of about 6 weeks. So it's quite convenient. It's not a completely inconvenient time scale. And that corresponds to the mass of the particle, the Compton scale. So there's Compton scale oscillation, which is of order of parsec scale. It's smaller than the de-Broglie scale, which is set by the momentum. So we mustn't get them confused. The de-Broglie scale structure is all here, including the soliton. But all of this field has to oscillate. And that oscillation is a pressure term in the general relativistic potential. So actually it's very straightforward to see the connection between the oscillation that's inherent to a scalar field and the timing effect. So the pulsars that we expect to detect in the center of the galaxy with SKA should be modulated by of order 200 nanoseconds on a time scale of about 6 weeks. So in other words, the arrival time of the pulsars will be speed up and slow down with an amplitude, a difference in time, a maximum amplitude of 200 nanoseconds. So if you average the times, you will see that the millisecond timing signal is either advanced or retarded on that scale periodically every 6 weeks, irrespective of which pulsar. But the amplitude is higher where the density is higher, because the pressure variation that adds to the gravitational potential is what matters here. See, this is the term that matters. You see that the scaling of this modulation in the potential is proportional to the local dark matter density. So this can't happen with normal dark matter. It's only because scalar field has an inherent oscillation. So this is the definitive test of this. But in the meantime, there are many other, as I say, lensing and dynamical ways, and perhaps other ways that others, I'm sure there's many ways of testing this that we haven't thought of. Very cold matter, gas should follow the wave-like structure of the dark matter, and that may show up in ways that we haven't imagined. So this is the conclusion that we've demonstrated that on large scales this light boson is indistinguishable from the usual heavy particle interpretation. It's cold. That's just because it's a condensate, so it's in the ground state and therefore not relativistic, despite the lightness of the particle. And then it gives rise to structures on a scale between 100 parsecs and a kiloparsec. And that there are various observational implications, as I've described. So the good news is something testable here, and that it offers an alternative to the undiscovered WIMPs. So, this is why I slightly cheekily chose the title of now being in the no-WIMP era. Because it's seemingly, despite all the stringent new experimental tests underground and in the LHC, it's neither been generated nor detected directly. So this provides that extra motivation for thinking of this cold alternative. Whatever the alternative to that idea of a heavy particle is, it surely has to be non-relativistic. So this is inherently non-relativistic, and by choosing the boson mass to be light like this, we can hope to explain a number of difficult problems that have faced regular CDM. The lack of small dwarf galaxies, the presence of large cores in dwarf galaxies, and also the rather late formation redshift that we're sort of getting used to because of Planck. So I think I'll just leave it at that then. Thank you.
Okay, thank you very much. Thank you. So, sure, there will be many questions. I don't know who was the first.
So, as you know, in all these problems at the low scale, cold dark matter solve it or try to solve it with the baryonic physics, the feedback, and so forth. So probably baryonic feedback is also important or relevant at some point in your simulation, or it will have to be included at some point. So I was wondering whether this also would affect your first estimation on the mass of the axion that you have estimated using the core, and how this could affect the rest of the results that you presented here.
Well, I mean, it all hinges on that mass. And so, we could have determined that mass either by the redshift of formation, or by the cores, or in some other way, pulsar timing. But we preferred to use the local dwarf spheroidal cores for testing this. And we've basically taken the view that this baryonic feedback is not a dominant effect on the formation of these cores. In this context, we don't need to invent anything baryonic to explain the cores. They're readily explained. But I mean, I know there are those who take seriously this this sort of resonant mechanism that apparently is supposed to somehow flatten dark matter cores, but personally I've always thought that seems a bit optimistic, because there's only gravitational coupling between baryons and collisionless cold dark matter. So how these, it's not like there's the pressure of the baryons is pushing the dark matter. It can't do that. Only the change in the gravitational field. So I believe that this as a sort of an idea of resonance that's meant to somehow create an oscillation that may give you at some time a flatter looking core, but for me it honestly seems a little bit optimistic, contrived, whereas here is inherent, so we wouldn't need an explanation like that.
Vasco?
I missed some comments on, for instance, forecasts for caustics and dark matter annihilation signatures, which would be expected to be different, right, due to this granularity, for instance. I guess that the merger history, the formation, and even the shapes of those halos may be different.
Yeah, they would be in detail. They would be different. Yeah,
they would be different.
Yes, a little rounder.
Yeah, they look rounder.
There would be less material in the outskirts because it's radiated away. This pressure term can cause a difference relative to normal CDM. Yeah. So you may find that structures a little bit more concentrated.
Yeah.
Although we don't have yet enough simulations and enough manpower as well, horsepower to test this all in detail. So, these are very good questions that we need to address.
Also, the cosmic voids seem emptier than in lambda CDM, and the filaments seem more pronounced, even though no halos form there. So I would expect that with Lyman alpha forest you could maybe test that against
right.
cold dark matter.
I see what you mean there. They do look sharper, these simulations, and whether that is...
They look emptier.
Slightly empty, but...
Lower density.
Maybe that the... the initial conditions here, I remember, have a kind of fine-scale pattern. And I think it's a sort of inherent to this gadget, to the way that the code is set up, that there is a sort of, seems to be a fine residual pattern that becomes noticeable when you compare these. So I'm not sure that whether they're really as empty as we imagine here by making these comparisons. But in terms of the forest, yeah, I mean I think especially 21 centimeter, if we could get into that regime of looking at structure at high redshift that's really cold, that then will show differences. We should see wave-like patterns and very, very sharp filaments relative to CDM. The filaments in CDM are thickened up by the relative motion of these small bodies within them, which is not happening here. It's empty. So, I think thermally they will be a little bit broader, and here colder. Yeah. So this is going to take ideally 20, because the forest is it's so relatively hot. So you've got to worry about the perturbations in the density delta phi compared with KT, the temperature of the gas, and since it's photoionized quite hot, so it won't feel. The ionized gas can't feel these small density perturbations that we want to measure, whereas the cold gas could do that.
Okay, and how about the peculiar motions of those halos? Are they different statistically from the standard?
I think not much, because the pattern develops in step. And so we haven't, you can see maybe there's some slight difference there, but whether that's numerical artifact or a bit hard to say. It shouldn't really have an effect. On a scale few times the de Broglie wavelength, the approximation to collisionless dark matter is exact. So that perturbations like you're talking about shouldn't really be present, I don't think. But we should, this all needs to be calculated in detail.
Jorge?
Somehow this is a question that follows up on Nacho's question before. And it is about how in the standard cold dark matter this problem of the core cusps in the dwarfs is solved.
Yeah.
Is the feedback of the baryons on the dark matter that
Wow.
produces.
But do you
arises.
believe that?
I mean, if you do numerical simulations with the proper feedback, you remove the cusps and you get cores which are comparable to the observed ones. And so actually that's the issue of my question. So in your field, you are sensitive to the gravitational potential. So you will expect to have some feedback from the baryons that are visible as stars, etc., onto your field. So somehow your simulations have to be modified by the presence of baryons.
Oh, they would show very big differences when baryons are present, but I think more on the
Yeah, but
the
what I'm
dense
saying,
solid
what I'm
ones,
saying
yeah.
is that then your kind of core
yeah.
will be modified exactly the same way as the cusps of the dark matter
Yeah.
are modified by the presence of dark
Well, I mean, I think
of
if you want
baryons.
to
So I
modi-
wonder
yeah.
whether that thing is going to be a problem or not.
Yeah. I mean, okay, let's suppose that you are somehow needing to expel a large amount of gas, and that this is done efficiently. Perhaps this is, then has these consequences you talk about. But if we just imagine that, the proportion of material there relative to the dark matter is inherently low, then I mean,
No,
there's
not at the
no
center.
direct evidence that for these dwarf spheroidals that they had such winds. It's not observed that they produced these kind of winds that you're talking about. So,
Because the prediction is not, I mean, we can talk about these things later, but the prediction is not in the dwarf spheroids they were now,
Yeah.
but how they were formed. And so that's what makes the difference. Now they are kind of quiescent and very inactive, and so nothing happened now. Of course, you don't see the winds now. The winds were there before. And so, at least, I rephrase my question. So, I understand that you have to consider in your model also the feedback of the baryons.
Yeah, we should. Yeah, and I think that will show up in the dense regions of more massive galaxies. We will see a lot of concentration and cooling of gas onto these dense solitons. So when we get to the stage of being able to include baryons, it seems clear that 10 to the 9 solar masses on a 100 parsec scale, which we're predicting for normal galaxies, would be a focus for a lot of gravitational condensation and cooling of gas. And so that maybe has a role in the formation of quasars. This is what we've been speculating. We made some basic calculations along those lines. But whether it'll have an implication for dwarf halos, I'm not quite sure.
Hi, I had a question to clarify the difference between Axion-like particles in dark matter and the quantum chromodynamics Axion particle.
Right.
Because the QCD Axion has couplings also with
Sure,
other
yeah.
baryonic particles. And I'm wondering whether you are considering dark matter particles that do not interact with baryons and only
Well, that's
gravitationally.
right. That's what we're assuming an axion-like. So the idea of this misalignment mechanism
Mhm.
is what's being used here. Rather, it's an analogy, if you like, with the QCD axion.
Right, and you said that the mass of the particle is your only free parameter,
Yes.
but that is after you fix the misalignment angle, right? Because you have to fix that angle so that you know how the particle is formed, the axion particle.
Well, we're just assuming that mechanism is inherent in the formation in the string theory context. So we don't model that. We just can say, well, all we really model is the self-interference of light bosons, of a Bose condensate. This is an evolution of a Bose condensate under its own gravity. And we definitely neglect all self-interactions that may be there. Because really we're interested in astronomical scale. So small scale self-interaction between any such particle would presumably be on much smaller scales and not relevant to this question of agreement or disagreement with the astronomical scales.
Okay, and would these axion-like particles be at all related with the so-called strong charge conjugation and parity problem of QCD?
Oh, I don't think so. No, you probably know more about that than I do.
Okay.
Yeah, I don't think so.
Okay, thank you.
Any other question?
Yeah, it's about the last part, about the kind of final confirmation, the timing
I mean,
to detect these intrinsic oscillations. I wonder whether, I have no clue, okay, of the answer. So I wonder whether this might be confused with the gravitational waves.
oh yes, that
are
would
going
be
to
the source
be
of noise.
kind of
indeed.
also producing this kind of changes in the.
No, I agree. I mean that
clocks.
is the source of the noise in that experiment, and we sort of tried to demonstrate that here to show roughly what that would be in this final plot. Of course, that is a stochastic background, whereas what we're looking for here is a monotone signal. It's a strict frequency. So the stochastic waves would be a broad band effect on the timing, and would be isotropic on the sky. Here, the signal will be proportional to the galactic dark matter density, and it is strictly monotone, just one frequency. So, but you know, you've got to find that frequency against the background of the gravitational wave perturbations. Now, the exact amplitude of those perturbations, the expectation for that is not clear, because it'll cause a model dependent on supermassive black hole merging. I mean, that's the dominant contribution thought to be, I think, for that. So anyway, we put this all in terms of the strain on a mass interferometer, and SKA should be easily able to detect the signal that we expect to see. But there is a background to worry about. We can, but I think it's hopeful that towards the galactic center, because that level, 200 nanoseconds, is already feasible to detect locally. You know, but we wouldn't see the signal locally. Locally, we'll only see around 1 or 2 nanoseconds, because the density of the oscillating field locally is so low compared with the center of the galaxy. So rho locally is small. So this effect. So, as I say, it's, from what I understand, there are millisecond pulsars locally that can achieve already a few tens of nanoseconds, maybe 20 nanoseconds detection, but of other things, right? Not of this, because locally you wouldn't, you know, you expect a signal that's lower than that, only a few nanoseconds. Okay, so 200 nanoseconds is what you. So the problem with these millisecond pulsars, detection in the galactic center is a bit difficult, because they're intrinsically not very luminous, and the radio background is high. But there are thought to be a few thousand millisecond pulsars in the region of interest within a few hundred parsecs of the galactic center, because of the scaling with a gamma ray wave background there. So that is thought that there should be plenty, and there are lots of young stars, as we know. Okay, thank you.
So let's thank Tom again.